Look at this landscape. These circular, layered mountain ridges appear perfectly still today, but they are the quiet aftermath of violent planetary scale collisions. The lithosphere, the Earth's rigid outer shell, functions as a mechanical ledger. Every push, pull, and tear from tectonic plates leaves a permanent physical record encoded in the rock. The primary objective of structural geology is to read that ledger. We take flat, two-dimensional surface observations and we reverse engineer the massive three-dimensional movements that shaped them over deep time. To translate those shapes, we must understand how crustal rock deforms. The entire process bifurcates based on two ambient variables, temperature and depth. Deep underground, extreme heat and confining pressure alter the physics of solid stone. Instead of breaking, massive rock layers will slowly warp, bend, and buckle under tectonic stress without fracturing. Near the surface, however, rocks remain cold and rigid. When forces exceed their strength, they shatter permanently. By mastering the physical language of both bending and breaking, geologists can reconstruct millions of years of invisible tectonic forces. Before diagnosing any rock deformation, its exact present-day orientation must be quantified. Our baseline is an undeformed, perfectly horizontal sedimentary rockbed. This represents the initial zero state. Tectonic uplift disrupts this baseline, leaving rocks tilted at unpredictable angles that require standardization. This brings us to strike. Strike is the exact compass bearing of a perfectly horizontal line drawn across the face of the tilted plane. The second coordinate is dip. Dip measures the maximum angle of downward tilt, dropping directly down from an imaginary horizontal plane. These two metrics are locked in a strict geometric relationship. The dip vector is always perfectly perpendicular to the strike line. Translating chaotic, angled outcrops into this uniform mathematical grid is the mandatory first step for mapping tectonic history. We apply this grid first in the shallow crust, where low temperatures keep the lithosphere rigid and prone to sudden failure. Brittle failure creates two features. Joints are mere fractures with zero movement. Faults are fractures where active structural sliding has occurred. The anatomy of an angled fault plane breaks the fracture crust into two distinct masses based on their geometry. The rock mass resting directly on top of the angled fault plane is defined as the hanging wall. The underlying mass, located directly beneath the angled fracture, is defined as the footwall. We can now apply mechanical stress. Imagine tectonic forces stretch and pull the regional crust apart, generating tensional stress. Under tension, gravity dictates that the unsupported hanging wall must slide downward relative to the footwall. We classify this specific downward displacement as a normal fault. It is the structural hallmark of divergent tectonic boundaries, where plates separate. Now shift the mechanical stress to compression, where tectonic forces actively crush the regional crust together. The intense inward pressure forces the hanging wall to be shoved aggressively upward and over the footwall. This upward displacement is classified as a reverse fault. If the fault angle is particularly low, it is known as a thrust fault. There is a third stress regime, horizontal shear. When rock blocks grind laterally past one another without vertical displacement, they form a strike-slip fault. Mapping these specific fault geometries directly reveals whether ancient landscapes were torn apart, crushed together, or sheared laterally. Let's descend into the deep crust where extreme pressure and geothermal heat alter the physics of solid rock. At these depths, intense lateral compression forces horizontal strata to buckle rather than snap, producing ductile folds. We identify the upward arching fold structure as an anticline, defined by its distinct A-shaped geometry. Anticlines follow a paramount dating rule. As surface erosion slices through the arch, it will always expose the absolute oldest rock layers in the geographic center. The opposing downward sagging structure is defined as a syncline, characterized by a U-shaped trough. The geometry here dictates the exact opposite dating rule. In an eroded syncline, the youngest rock layers are preserved in the center. If compressive stress continues unabated, these symmetrical folds can tilt over entirely, creating recumbent nappies. These large-scale folds serve as the crust's plastic memory, permanently encoding the direction and intensity of ancient compressional forces. We can synthesize these mechanical rules to diagnose a complex real-world geological artifact. This is a geological cross-section diagram showing a localized slice of the Earth. We'll use it to begin a forensic analysis. Direct your attention to the prominent vertical fracture on the far left side, which isolates the block containing layer A. Look closely at the geometric relationship. The hanging wall containing layer A has clearly dropped downward relative to the adjacent block. Because the hanging wall dropped, we can definitively diagnose this left side fracture as a normal fault, indicating a specific period of regional tensional stress. Now shift focus to the deep strata layers at the very bottom of the diagram, below the surface sinkhole. These rippling structures are ductile folds. Mechanics tell us they could only form under immense lateral compression at depth. We can deduce the sequence of events. The deep compression and folding must have occurred first, before the rigid, brittle faulting fractured the region. Transitioning our analysis from a 2D cross-section to a top-down, real-world satellite topography view yields similar insights. Observe the specific dip of these rock ridges. Notice how they slope inward toward the central basin. Mapping this geometric orientation to our fold models, the inward dip identifies the basin as a classic syncline structure. Millions of years of weathering have simply shaved the top off the fold, creating a massive erosional syncline. By mapping these specific geometries, we resolve stratic landscapes into a chronological sequence, reconstructing the tectonic pulses that drove planetary evolution.